Hello boys and girls, in this video we're going to talk about the Bessel correction and the sample variance and the expectation of the sample variance. To hook you, I tell you something from the world of Python that you might not be aware of. So what I do here is I import four libraries: statistics, pandas, torch and numpy. And I use numpy to sample 20 values, n equals 20, with random.random from the uniform distribution. These are values between 0 and 1. So here we see there is a bunch of values between 0 and 1. We have these 20 values. And now here prepared, I have four ways of computing with these four libraries the mean and the standard deviation. If I copy paste this in here and we look at the means, okay, we saw the mean of these 20 values between 0 and 1 happens to be 0.485 something something, and all the libraries agree on that. I mean, here it's abbreviated, but it still agrees. But if we look at the standard deviations, which happens to be 0.268 something something, then what is weird is that the numpy value is actually only 0.2613, right? So there's a difference between, for example, pandas and numpy. And this difference, this error, we will say in which sense it is an error, is actually systematic. The implementation for the numpy function standard deviation without extra arguments systematically underestimates actually the standard deviation. And the standard deviation is the square root of the variance, so also the variance is underestimated. And it turns out they use a formula which has a bias toward getting a smaller value. So this might be a source of, if you do implementations of some statistical stuff with these libraries and you get two results even though you use the same thing. You use STD, but then it depends on which library you use what you actually get. So this is good to know, and we will explain in this video why that is. In a sense, why the statistics library's implementation is sort of the nice value in a theoretical sense. Although I take, I say quotes always under quotation marks, because if you have more and more samples, then these values would converge to each other, as we will show in this video. And all of the mathematical functions and implementations, they have their own properties. So I don't want to say good or bad, although there's a sense in which this statistical library, the unbiased variant, is the nicer one. Here is also some values which you can try at home and which we will come back later in this video. If I hardcode the sample basically to these three values, 15, 17, 19, I have chosen this in a way that the difference between the first and the second and between the second and the third is the same value. It's 2 in this case. Then the mean is 17, of course, it's the value exactly in the middle in this case. And the standard deviation turns out to be 2, which is also happens then to be the actual difference between these values. Whereas if you compute this with the numpy library, then you will find that the standard deviation is just 1.6 something something, right? So there's again the standard deviation that it computes for this fake free value sample is actually smaller than the actual difference between these values. And so the standard deviation is just the square root of the variance. So the standard deviation is the square root of 4 in this case, 4 or 8/2. And for theoretical reasons, as we will see, like the formulas that are implemented here, the numpy variance is actually 8/3 and not 8/2. There's this difference of the denominator that is used. This is exactly here the wrong one is exactly the number of sample values that you have here, and this is how this comes about, and what we are going to explain. Okay. So before we get into any sort of proofs or statements, just some definitions I want to make. The definition of the expectation of a function of some random variable x, capital X here. In this video, watch out for capital X versus small x. The expectation of f of capital X is the sum, or in the continuous case, the integral over all possible sample values, everything that's possible, of this value weighted by p of x, and this weight in the stochastic theory is the distribution, the probability distribution for each individual value, right? Okay, and then the star of this video is the variance. The variance is an expectation, namely you take the random variable itself, you subtract the expectation of the random variable and you square it, and you have a function in terms of the random variable, and the expectation of that thing, that is the variance. And then the standard deviation is the square root of the variance. We are not going to care for the standard deviation anymore. We're just going to talk in terms of the variance in this video. Okay, so these are the definitions. Now, here the first definition that is relevant in this video is that of the sample mean. So if you have capital X, this is the random variable which encodes, like the associated distribution encodes this random process, and we're going to take this sort of frequentist perspective that this is like a process from which we can sample and reconstruct the probability distribution. So we take samples, we are able to sample, for example, with the NumPy library, we take 20, n equals 20 samples from the uniform distribution in this case, but our discussion will be general. So we take 20 samples, and then if we have n samples taken from one random variable, then we define the associated sample mean for this set of sample values as basically the average of this, right? We sum over all the samples, over all the actual values, small x that we got, divided by the number of samples. This is denoted here by x bar. And this is an estimate for the expectation in the way we defined it above, right? So the sum or integral over the value over all value small x times by the weight, the probability weight, is the expectation, and the sample mean is one estimate of that, right? And it, like by stochastic theory, it will be the better the more samples you draw. Okay, further, here we have now another definition. We had just had the sample mean. We now talk about the sample variance, and it is defined as such, and the video is about why it is defined as such. The sample variance is the sum over all sampled values, over all sampled values of the square distance between each sample and the sample mean that we have just defined, divided by n minus 1, this number of samples subtracted by 1. So the claim is that this thing with 1 over n minus 1 is a good, we will see like a more formal definition in a second, is a good estimator for the variance here, right? In the same sense that the sample mean is a good estimator of the expectation, the true expectation, which we could like analytically compute if we had the exact information what the probability distribution is. In the same sense that this is a good estimate of that, this thing is a good estimate of that. And now the strange thing is to be explained, why is it not like here 1 over n, right? If this is the way to estimate some expectations, why not in this case also here? And the TLDR is, the reason is that in this formula here, right, if we make 20 samples, if we draw 20 samples or 9,000 samples, whatever it is, let's say 20, then we say here the samples play a role, and what we subtract here on this other side, this the sample mean, which is used as an estimate in the formula for the expectation, then here for the sample mean we are reusing, or we have reused all the sampled values that we are also using here. So right, we use every sample actually twice, and as we will see in this video then, or as we'll argue at the end, this introduces a bias, right? We do not here, for example, take 40 values, use the first 20 for estimating the mean and estimating the expectation, and doing the 20 subtractions from that one value. But instead, we are more efficient, right? We only sample 20, and we use each variable in this formula twice, right? This each variable divided by 20 pops up here and is used twice in this way, right? So this is why you do not want to do what you do here, right? In principle, you would say, okay, if m estimates, as a new variable, if m estimates the expectation, then in this way I can estimate the variance, and you can. But the issue is here that this m is not like estimated from other independent samples, but actually in this case the x bar reuses everything that you also use here. Okay, I hope that makes sort of sense. We will see then we will see it formally, and we'll also give an argument at the end why using 1 over n, if we would use that, you also get something, right? The difference is only n minus 1 over n, right? This is the difference between these two sort of formulas if you were to use x bar for m here. So if you have enough samples, then this goes against 1, and in this way both of them in the limit have are good estimates of the variance. But if the sample is not gigantic, then this like in this case you saw with in NumPy, in general, if a finite number of samples, this is always an underestimate. You always are a little bit lower in this way, right? I mean, it's clear from this, because if the number n is bigger than number n minus 1, and therefore if you divide by bigger number, you get something smaller. And we will argue that this is in some sense even the minimal estimate with respect to these formulas. Okay, I'm going to come back to this intuition in the end of the video, but now we come to the formal part of the video. The statement is that the sample variance formula, the one with the 1 over n minus 1, is an expectation equal to the variance, which is the expectation of this, x minus expectation of x squared. So in this way, it is good or correct that the expectation of the sample variance, this variance obtained from samples, this object is in expectation the actual variance, and has the right fraction in front of it. Okay. Here I do this proof in 2 blocks. Okay, I'm going to do the second, explain the second block first, because it's easier, and then we do this sort of more nasty refactoring as a second part. Okay. Okay, before I actually go there, just so that it is conceptually clear, right? So I'm talking in the whole video from one distribution, one underlying, if you will, probability distribution that we draw a bunch of samples from. We are free to draw samples from it. So for example, from the uniform distribution in the Python case that I showed you, we draw 20 samples. So there is a random variable which is associated with this distribution x. And to talk about samples, 20 samples, for notational convenience, let's say, we split this one random variable that we have up into 20 copies, and we will talk about these 20 random variables, which however are identical to the x, right? All of the, for example, if we fix n to 20, we have 20 different random variables xi, but they are all basically the one random variable that is here. We use this mechanism to talk about independently drawn samples in a formal way. So this is always done. You have always this independent and identically distributed random variables. So identically distributed because they represent the same x, and independent such that you can talk about independence properties. Okay. I don't actually need any stochastics theory here apart from these small properties here, these two properties, because in the end it's a counting argument. So if we take two indices, right? Again, in the example, let's say they are between 1 and 20. If this index denotes the same value, for example, I equals 17, then this expression here, the expectation of x17 times x17 is the expectation of x17 squared. And because all the xi's are identical, we can, without loss of generality, talk about the x1, the first one, right? Okay. Whereas if these are different indices, then they are formally different random variables, and drawing the samples is independent. And so by the rules of stochastics, it derives that this is then the expectation of x squared, right? So in one time the square is inside and the other it's outside, depending on the indices. This is the only thing we need from stochastics basically here. Okay, so the formula that we want to derive is the statement that the expectation of this combined random variable, right? This is a random variable made up of 20 random variables, like 1 to n. This thing divided by n minus 1 is indeed the variance. Once we have this, then we have that this object that we have defined, the sample variance, in expectation is the same value as the true underlying variance, right? Okay, and this part is simple apart from this final step. So here we have the expectation over this object that we have just defined, right? This is this xk. The index k is not bound, so this is one of them. Whereas here we have the sum over the 20 random variables and divided by n. This is exactly the model for the sample variance. We can pull out the sum here. Then we multiply by n over n, and we pull out the n because there's a square, this is squared. And then because j binds this index here, the sum binds this index j here, and k is like any of the identical 20 random variables. This is just going to be 20 times this expression. So one of the n's cancels, firstly. And then the only thing that we actually have to compute to get to the final result is the statement that this thing here, this expectation, equals n times n minus 1 times the variance. Okay, and this is the more complicated part of the proof. So this is the object that we want to simplify to see how it relates to the true variance. So okay, this is like a squared sum, right? We can double the sum here. We introduce another index j, and the other index is going to be l for these expressions. And now we have to count. Basically, we want to split this into two parts. The one where the indices coincide, and the other where the indices are different. And now we just take a close look and do the counting. So and now I mean, this is this long line, and you can see what the translation is. I'm going to tell you the first arguments here so that we don't drag it out too long. But you have first this again, this k is not bound here in this formula, right? This is either one of these k's. So you have here xk squared, which without loss of generality is the same in expectation as x1 squared. And you have it n squared times, because the sum goes from j from 1 to n and 1 to n. But this is not dependent on I or j. So we have n squared times k squared. So n squared times x1 squared. And then, you go on. You take this fixed k, and you see how often you get xk squared with this index xl, right? Which are the cases in which the l just equals k? Well, out of the 20, there's one case where the l equals k, and the other sum over j is doesn't matter. So there's n times one of these combinations, and this x with this and this with this. So there's 2 times this situation. So we have 2 times n, and these have a -1. And you can do these arguments in your head. You can do the counting. When do the indices ever coincide? When are they the same and when they are not the same? And you get these counting expressions. And then you find, oh, both of these expressions are actually n times n minus 1. And so we have the cases where the indices coincided and one where they not coincide. And here I have a typo. This should be on the outside. Otherwise it would be 0, right? So there's a typo here. And this is exactly the variance. And therefore we have shown what we wanted to show, QAD. So we found, again, I repeat, the expectation of the sample variance is exactly the true underlying variance. And if we divide by something else than n minus 1, well, then we are over or underestimating it, right? For more and more samples, the difference between this will go towards 1, so it will vanish if you have more and more samples. But here this theorem says that how many ever samples you draw, you are weighting this value that you compute with this formula exactly right, so that you can that you have a good estimate of the variance. Okay, so finally I want to argue why the other approach would be an underestimate. So again here the intuition for why this is always systematically underestimating the variance. Well, okay, again, if E, previously I called a similar variable M, if E estimates the expectation, then we might naively think about using this formula for the estimation of the variance. And now to see why this is minimal in some sense, consider the case where you only have 2 samples, right? Then this formula would be 1 over 2, and then the sum of 2 terms, it would exactly be this with x1 minus e and x1 minus x2 minus e. So I ask a naive question, hey, for which e is this thing actually minimized, right? To compute that, we would take the derivative of that, right? Chain rule, 2 comes down. And we find that the minimum is exactly when this sum that we have here equals 0, which is to say when e is exactly the average of x1 and x2, right? x1 plus x2 divided by 2. So when we take e to be the the sample variance, then this expression is exactly minimized, right? So with respect to whatever we use for the expectation of x, which value we take, we exactly minimize that whole thing if we use the sample variance as the estimator here, right? So in this sense, like the estimator of x, the estimator of the expectation of x chosen to be the sample variance exactly minimizes this, and this is the sort of problematic aspect where then this bias comes in. Okay, I hope that sort of makes sense. Do I have it with me here? I'm currently reading the motivation why I thought about doing this is it is mentioned shortly also in this book that I'm reading, which I'm quite enjoying, explaining Monte Carlo methods by Dunn and Schultes. And they mentioned that, and I've seen this a couple of times, and there's also a bunch of YouTube videos on there, and then I've looked at the YouTube videos that cover this Bessel correction, and they are all doing vague discussions in terms of samples and trying to give you an intuition. And there's a way of talking about this in terms of the bias being introduced by having too little degrees of freedom and such. But I actually never seen this sort of stochastics theory derivation, and I hope it's convincing. Okay, with that said, I wish you a beautiful weekend.